Welcome back. Today's topic is going to be about transfer functions. Transfer functions can be written in a form like C of s over R of s is equal to be G of s. Capital G is usually used for transfer functions. And then the numerator and the denominator. In the numerator, we use the coefficients b, like bm for instance, and then the complex variable s power m plus bm minus 1, s to the power m minus 1, and so on, plus b0. And in the denominator, we use the variable for the coefficients a, and the subscript is n, s to the power n, plus a n minus 1, sn minus 1, you've guessed it, plus plus plus, a naught. That's how we write on transfer functions. So in a block diagram setting, it has to be written like such. R of s is the input to our system. Then you have a block, which is basically this whole thing. The whole g of s is inside here. And what comes out is cs. That's very simplistic what the transfer function is doing. It's taking input r, going through the system g, which is prescribed by numerator and the denominator, and the output is cs. Now, it is time for an example. In my case, I'm using a spring mass system where m is equal to b1, c is equal to b0.1, and k is equal to b1. So the system looks simply like this. You have a spring, stiffness k, you have a dashpot, damping constant c, and the mass m attached to this with the displacement x and an input u. Very simple. Now, the differential equation for such a system looks mx double dot plus cx dot plus kx equal to be 1. Because 1 in my case is the input, I'm just making this a step input, very simplistic. It's going to be constant over time, so it's easy to transform into the Laplace domain. I should mention as well that the initial conditions in the beginning, the position and the velocity are both 0. That makes the transformation much, much simpler. I start the problem by writing down two very important Laplace transformations which we will need to solve this equation. The first one is going to be a e to the power minus at cosine omega t is going to be equal to a s plus small a divided by s plus a in brackets squared plus omega squared. That is the rule number 1 which you'll need. And rule number 2 which you'll need is the Laplace transformation of something very similar, except we're using a sine. Omega t is going to be equal, we know what, we can name this variable b. It's going to be equal b omega divided by s plus a squared plus omega squared. Now, I'm mentioning those because we will need those later to solve this problem. I'm starting off by putting the Laplace transform on this problem. Now, applying the Laplace transform on this problem will result in s squared, and plugging in obviously the variables which are given, s squared xs plus 0.1 s xs plus k is equal to be 1, just xs equal to be 1 by s. Okay, this is a problem which we have so far. Now, let me shuffle the equation a little bit around by putting the xs on one side and all the rest on the other side. If I do so, the equation can be simply written out as 1 divided by s, that comes from the step input here, and s squared plus 0.1 s plus 1. Now, I can work with that equation. What I can see first is that the root of the denominator, or people say the pole of the transfer function, is situated at 0. The second and third pole can be calculated very simply, and I can give it to you now, but you can do it at home as well if you want. It's 0.05 plus minus 0.9987 I. I is imaginary number. So from here, I know I have complex roots. So to apply the partial fraction on this equation, I can simply state that xs needs to be, if it's 1 over s squared plus 0.1 s plus 1, it needs to be equal to k1 over s plus k2s plus k3. In the denominator comes s squared plus 0.1 s plus 1. Let me write down, first scenario, I can multiply everything by s. If I multiply everything by s, on the right hand side, I'm having k1 over s multiplied by s, which results solely in k1. And this whole side is going to be k2s plus k3 multiplied by s. So I'm just writing out the right hand side now on this. So right hand side multiplied by s. This results in k1 plus k2s plus k3 s squared plus 0.1 s plus 1 multiplied by s. Plug s equal to be 0, because that is one root which we have. I plug in s equal to be 0, and what you can see from the right hand side, only k1 remains. Now on the left hand side, what remains, if you multiply this and you plug in, is going to be a 1. So the left hand side is going to be a 1. This means k1 is equal to be 1. Very simple. So now I have to multiply this whole equation by s squared plus 0.1 s plus 1. And I'm doing so I can claim it's going to be 1 over s equal to be k1 over s multiplied by s squared plus 0.1 s plus 1. And the denominator from this side and the numerator, if I multiply by the same thing, are cancelling simply out. So I'm only left with k2s plus k3. Okay, so far so good. Now I'm choosing to plug in the positive root of this equation. So plug s equal to b minus 0.05 plus the plus sign, that means positive root, 0.9987i. If I plug this in now, what do I get? I get 1 over minus 0.05 plus 0.9987i equal to b. I'm saving a bit space here because I know if I plug in this root in this equation, which comes basically from the denominator, this will completely go to 0, and it doesn't matter whatever is in the denominator, except this is 0. But this is not a 0, so this is valid and simply 0. So the whole term of k1 vanishes. So I'm only left with k2 multiplied by minus 0.05 plus 0.9987i plus k3. Okay, now I leave this up to you. I don't need to solve this equation. I think you can do that. It's basically multiplying with a complex conjugate on this side, solving for k2 and k3 by equating for the real and imaginary term. You can do that yourself because it's pretty tedious. So k2 is simply minus 1, I should say approximately minus 1, and k3 is minus 0.1. So now we have our equation given. I'm going to erase this and just write down what we derived here on this side in this equation to make your life simple. So let me erase this right now. I'm applying here, I'm splitting up this mess into 1 plus s minus s over s squared plus 0.1 s plus 1 minus 0.1. I want to have this s and the constant being separated, which happens right now. Okay, that's good. And what I can do further is with a quick glimpse, I can claim that the denominator of this function is s. Remember, I want to have it in the form kind of like this, s plus a in brackets and then squared, s plus 0.05 squared plus 0.9975. And I can do the same thing on the right side here. S plus 0.05 squared plus 0.9975. Now, once I have this, I have to see how can I use this theorem here. I have an s, which I will not get rid of, so I have to probably use some cosine on this term, but there's something missing here, that's this plus a. How can I get this? Now I need an a which is similar as in the bracket. So I'm going to subtract a minus 0.05, but if I subtract from the right hand side, I need to add as well. And this will basically look like this. I'm just writing it in one equation because I'm not writing down the whole equation again. It's going to be in total subtracting because this minus makes this plus a minus. So on the right hand side, I have to subtract, and let's end up from 0.1 to 0.05. Now, okay, I have this given. What do I need to do next? Next, I need to bring this variable. If you look at omega squared, this has to be very similar to this one here. Now, I can do a little trick here by deleting this number, make it 87, and take 0.9987 squared and put a 0.9987 right here. And I just have to consider how much of the 0.05 needs to be added when I multiply by 0.9987. It's basically adding this omega right now here, but the b has to be adjusted accordingly because I want to have the same number here, and it's just the smallest adjustment. It's going to be 501. Okay, now I'm done, and I can actually apply those two important theorems from the beginning which I had here. If you see, this is theorem 1, and I forgot to make a label here. This is theorem 2. Okay, so let's apply that. On a step input, simply the x of t is going to be just a 1, so it's an offset, and then I'm going to have this one applied here, which is simply e minus 0.05 t cosine of 0. Oh, I forgot one important thing. Sorry, I did the mistake. I need to get this one as well squared, which is an 87 squared. So that's going to be 0.9987 right there, multiplied by t, and then minus 0. That's now the b. The a here was 1, but here the b is actually 0.0501 e minus, and then whatever it is in here, 0.05 t multiplied by sine of the omega 0.9987 t. And this equation can be modeled in MATLAB, and I want to show you again that if we how to plot this function compared to an ODE. If you have an ODE, you can simply simulate the system with a differential equation in time domain. But if you go over the Laplace domain and then bring it back in time domain by finding the solution, this is a closed form solution which is much faster to solve than modeling it numerically. Okay, we start the problem by simulating this in ODE. Now, initially we need to clear the workspace, we need to clear the command window, and we close all previous figures, even though I don't have one, but that's fine. I'm starting off with the closed form of this problem. By looking at a vector, I'm going to simulate lin space between 0 and 100 maybe, and have 101 elements. That makes, again, the spacing very even. The spacing is going to be then between 0. and 0.1 increments. Okay, then I'm saying I want to show you how much faster this closed form is compared to simulating it with ODE. So I'm having a tick, and I'm combining a vector where I'm saying I'm having a vector now, which I'm naming 1 minus the exponential. It's basically 1 minus exponential minus 0.05 multiplied by t vec, and this is going to be multiplied by the cosine of 0.9987 multiplied by t vec. It's going to be this guy. Why do I do a dot product? Because I'm having a vector inside a function which is sine or cosine, and doesn't know how to take it. So that's why I'm doing a dot product, because I'm having a vector in one command line defined. Okay, I'm doing a line switch here, and I'm saying minus 0.051 dot product again, exponential 0.05. The same story as up there. T vec multiplied by sine of 0.9987 multiplied, a lot of dot products here, T vec. Okay, that's it for it. And then I say time elapsed CLF is going to be TOC. So TOC basically saves my stopwatch, and I'm saving this in time elapsed for the closed form. Now I'm going to tackle the ODE. So ODE is going to be this one. I'm having my initial conditions, which I have to define. They are going to be 0 and 0. And then I have my options. I have options are the ODE set, and I'm having relative tolerance of 1e minus 8 and absolute tolerance right here, what this is written. Yep, I just need the apostrophe. And this is going to be equal to be 1e minus 8 as well. And close this comment, okay. I'm having a tick. Give ODE fair chance kind of, because initial conditions and defining options shouldn't be in our counter. So I'm saying tick, and then I'm saying big TT and XX are going to be my ODE 45, which I'm calling now, and I need to be careful. I'm going to pass an argument, which is T and X, and I'm making a function up, FCODE, which passes only those two. And I want to have my time vector, of course, my initial conditions I need to be providing, and my options. So once I have this, I can look, that's going to dive into the function. But afterwards, I have time elapsed, not CLF, I have time elapsed ODE, and this is going to be my TOC. So this is my stopwatch again. And for later, I want to save my variable, and instead of xvec CLF, I want to have save xvec ODE for my first whole, because the rows are going to be each timestamp. The first column is my position, my second one is my velocity, but I'm only interested in the first column. So now it's time for me to dive into the function, and the function looks, I make a little thing here called functions, and I have function, it's simply dxdt is going to be equal to function ODE, function ODE, yeah, it's not the English one, ODE, t, and just make it straightforward, is xvec, and I'm having xd is going to be simply my second entry of my vector, which I'm passing through, and my acceleration comes basically from here. So what I'm doing now is I am modifying this equation to be x double dot is equal to be 1 minus, well, m is 1, so that doesn't matter, 0.1 x dot minus x. So that's basically how my acceleration, that's how my whole system gets driven somehow. And the input shows up right here. So it's going to be 1 minus, equal sign would be nice, 1 minus 0.1 multiplied by xd minus simply a 1, or I leave it as this, xvec of 1. So that's basically the position. Okay, now this is done. I just need to pass this to dxdt, and that's going to be equal xd and x double d. Okay, and ending my function right now here. That should technically do it. Okay, we can see if we run this, what happens. If there's an error, probably is an error, tapping it down like just in. Okay, all good, run through. I want to plot that. So for plotting, I need to different section, and I'm having, furthermore, I want to print fprintf. I want to say percent of computational time CLF versus numeric, and I'm gonna define a float for that in percent. How much is, I know that this one is faster than ODE, but how much faster? So how much is this of the ODE simulation, I should basically say. And this is going to be happening by time elapsed CLF multiplied by 100 divided by time elapsed ODE. Okay, so that will tell me basically how much time has elapsed. Now let's see. if I look at my command window, oh, I forgot probably something very important. That's a 4.2f. I want to have a float. Okay, so now 0.31%. So 0.31% is this computational time of simulating this in ODE. That's more than 100 times faster, which is insane. Technically even more than 200 times faster. So let us plot the result. I mean, I can tell you a lot of stuff, but we want to really see if those results, if I plot them overlapped, actually overlap and work out together. So I'm going to do that. And for this, I'm going to have figure 1 is going to be this one, and I want to hold on to that. And I'm going to say plot, I'm going to do a lot of shortcuts here, but xvec clf, and name it B, is for blue. And then I'm going to copy paste the whole thing over here and make it red dashed so I can see the nice overlap between those two. And this is the ODE. X label, I'm labeling this even for you here. It's going to be the time in seconds. And this one, and this one is going to be the Y label. And this is going to be the position, or Y label can be, I'm naming it X as a state, or yeah, we can name it X. Position X, because that's what I basically had, XT. Okay, and the legend, first we plotted the closed form, and then we plot the ODE. Okay, or I should say it's numerical technically, numerical. Okay, now I'm saying grid on, and I want to set my background to get current figure. I want to give this a white color. That's just for beauty. Okay, now let's see what we have until here. Keyboard, because I want to show you afterwards something even cooler, like an animation. Make some extra space here that I can bring to the top. Okay, so let's see. We know it's faster, but is it actually the same plot? Let's see, the plot is right here. Oh, something is not working out well. I probably forgot or messed up the sign or something like that. Closed form. Closed form grows again. Did I mess up a sign? Yep, I messed up a sign. See, I do mistakes too, so it's a live coding session. It's only minus, but still that messed up our code a bit. Okay, so editor, I want to run this again. F5, run again. It's nice to see as well the minus here with the that this term gained power more and more over the time, but in the beginning wasn't visible because it's having this small b here in front. But yeah, anyway, the solution, you trust me, is the same over 100 seconds. I could do 1,000, 2,000, it will still be the same. That means our algorithm actually works out. And yeah, so now it's, I think, time for some nice animation, which I always like personally because it really shows me how to do things. It's going to be more complicated. You can skip out of the video here if you're not interested anymore. If you want to see the animation, stay tuned. Like, I would be happy to show that to you because I'm putting actually my effort in this. But the idea is having a wall color, making it 200, 200, 200, dividing by 256. That's the color code, actually 255, because that's how many RGB colors are in the thing. Then color of the mass. I want to make this a bit distinct from the wall, so I'm making this 150, 150. Okay, and then I'm saying F2, my figure, is going to be figure 2. I'm defining this because figure 1 is my plot. And F2 position, we can adjust it later. I'm just putting this as a placeholder right now. It's going to be, let's say, an X600 and then 100, and I say 400 wide and 400 in height. That's okay for now. Yeah, so I'm having a for loop because I want to go through all the different time steps. It's going to be 1 to the length of tvec. Here's an end in the end, but I need a subplot of 1 to 1 where I want to show you this one subplot, and then I have rectangle with my position going to be equal to be in that plot itself of minus 0.1. It's a bit, okay, 0, 0.1, and 0.5. And then I'm going to have a face color for that. See, it's already suggesting it. The face color is the color of the wall. And edge color, I'm making none. So none. Okay, that's fine. And then I have the same thing. Now I'm just repeating this. I'm a bit lazy. I'm copying just that over. And here I'm having a 1 plus xvec CLF of my current time, where my mass basically would be. And minus 0.2, you will see later why, 0.4 in length and 0.5 height. Okay, no, face color is now face color of the mass, and the edge color should be none. Okay, and then the axes, I'm going to put this in minus 0.2, 3.5, minus 0.1, and 0.6. Okay, so that makes my axes kind of nicely adjusted to that. And then I'm saying I want to model the spring as well. The spring is actually simply modeled. Each time I need to model the spring, I need to model the zigzag maneuver, okay? So I'm having 1, and I'm saying I want to have 10 of those. And I say the distance between A and B is nothing else than 1 plus xvec CLF int minus 0.2 divided by 10, and my temp variable b, which I'm just defining here right now, is going to be int multiplied by distance of AB. Okay, and if, because I have to go up and then down, so it makes sense when I say if the modulus of this one is divided by 2 and it's going to be equal 0, I'm going to plot simply, temp A to temp B, and then I say 0.5, 0.4, and I want a pitch black. That's okay. I'm going to copy this one. Else, I'm plotting from 0.4 to 0.5, so the opposite in height. I'm going down. I'm going up. Okay. Now this is good. I'm saying and here, and then I say temp A, it's going to be temp B. Okay, good. Now the damper, that's another story. First and, because I'm done with the zigzag, the damper is going to be plot, that's just basically putting a little small rectangle for you now here. It's going to be 0 to 0.1, comma, 0.1, 0. I'm just making a little rectangle here. Could be probably done easier, but that's just the way I do it. Okay, and I'm gonna copy this time 4 times, and I'm gonna adjust it a little bit to 0.1, 0.1, 0.1, 75, 75, 0.1 is fine. Here 0.03, here 1.7, 0.3, voila, 0.3, okay, and here 0.3, and here 1.7, and here 1.7. Okay, that's good. And now I need to plot some other stuff as well. I need to plot the damper itself, moving. So plot, my PC will probably not be even fast, so you can see that nicely moving. Plus xvec CLF int, this is another bracket which should be there, divided by 3.5 minus 0.8 minus, and then a space, 1 plus xvec CLF. I'm just using a closed form expression for this one here, minus, come on, 0.2. Okay, line switch. Okay, and I'm saying 0.1, 0.1, and again, pitch black. Okay. So that's going to be this one, Control I, closed form 3.5 plus, and then this one as well divided by 3.5 minus 0.8. Okay, and here I'm making this a little bit different. So basically dimple going up and open and close. That's basically the idea here. Okay, and then not done yet. I need to still plot an arrow. So plot arrow, plot, you know what, for this one I'm actually copy erasing this from the damper over here. That makes it much faster, rather adjusting than typing everything down. So 2, even though it's a lot of adjustment, 0, 5, 0, 5, 0, 5, plus 0, 5, all negative, negative 0, 4, 0, 6, negative, negative, here 1.8, 2. Actually, this will not work because if I got a closing bracket here. Yeah. Okay, this one, this one, this one, and here a closing bracket as well, here as well, here as well. That should look better now. Let's see. This can be gone. Oh, that's why I messed up big time here. Oh, that was bad. Okay. Okay, this one here, this one here, this one here. So now almost done. 1.8, 1.8. That's going to be 0.8, and that's going to be 2. Okay, that should be everything as minus forgotten here. Okay, and then I say, actually this one I didn't really need. It's saying text. I want to see a text 2, minus 0.08, and I want to see the x of that. That's the arrow basically showing, and then a font size. Font size of 30. Okay. Okay, font size of 30 is going to be closed here. Now, again, axis off, and subplot. Oh boy, okay. Subplot of 1 to 2. I'm getting tired. Sorry, it's like a lot of lines here. So plot tvec from 1 to in. So I want to just plot until the current progress, not more than that. Xvec CLF. Yep, take that 1 divided by int blue, and then x label. It's basically just showing the thing over time. Time in seconds. Y label is simply position x, and the grid is on. And then axes, I want to plot between 0 and 50 with a height of 0 to 2. And because my plot might be fast, I'm going to pause it as 0.01, even though I don't think my laptop is going to be fast. And then I say, clean my current figure. Let's see if that runs. Okay, the keyboard is good. Let's go continue. That's now my plate. There's probably an error. Yep, I heard an error message. Temp A 47. Okay, there's an arrow. And then 47 makes sense. The spring should be initialized with 0 as per the last error I'm having in this code. Let's see it again. I'm deleting this keyboard here because it's just not necessary anymore. Okay, so let's see. Here another X label. Oh yeah, that was definitely typo here, but it's not a big typo. Okay, let's see now what happens. Yeah, it's way too fast. Let me make this a bit slower. So 0.1. Stop. Okay, let's do it again. Let me adjust this for you a little bit, 0.5, and let me adjust the position a bit for you guys, so you can actually see it much better. Make this 700, make it a bit wider, and a bit higher. Okay, that should put it more on the frame, so you can see it. Okay, here we go. So we see the dashboard moving nicely. The spring worked as well, the wall's on the left, the mass, and the position X goes on the right side. So everything works out, and that's basically our closed form solution. I can show it to you again. I like those animations because they really illustrate the problem and they really make you feel you understand MATLAB and what you're coding up. And as well, coming from these kind of equations, I think as control engineers, it's very important to as well being able to picture the problem. Okay, the time is up. I really enjoy teaching you this material. And if you feel that this is valuable material to you and you like what I'm doing on the Lightboard and my live coding sessions, please leave a like or subscribe to my channel. That would support me, and I am happy to see you the next time.